In this video, I want to explore how and why standing waves occur. Standing waves are actually a combination of two moving waves coming at each other from opposite directions. I want to explore this phenomenon on a string that is clamped at both ends and is being driven by some sort of oscillator. Remember that when the wave reaches the clamp, it gets reflected back upside down. To make a standing wave on a string, there is a particular synchronization between the vertical motion of the oscillator and the horizontal motion of the wave which needs to occur. When the oscillator has completed 1/4 of its cycle, the wave should be exactly halfway along the string. Continuing on, when the oscillator has finished half a cycle, the wave should arrive at the clamp. Remember that the returning wave is going to come back inverted. When the oscillator has finished 3/4 of its cycle, the leading edge of the wave is now back in the middle of the string, traveling leftwards, having covered a distance of 1.5 times the length of the string. The reason the right half of the string is flat at this instant is because the returning wave and the trailing edge of the original wave are cancelling each other out. Continuing on, you can see that the leading edge of the wave gets all the way back to the starting point, having traveled a distance twice the length of the string. And here is the key point. This leading edge must arrive back exactly as the oscillator finishes one period, because now the wave is going to be reflected and flip upright again. You can think of the arm of the oscillator as a second fixed end. If the wave is flipped upwards as the oscillator is moving upwards, it is going to reinforce the wave, and the result is a standing wave. To describe this mathematically, first consider the period of oscillation of the oscillator, which we will call T1. This is the time for the oscillator to complete one full up, down, and back up again motion. Compare this time with the time it takes for the wave to travel all the way down the string and back again to its starting point. The time it takes for the wave to travel there and back can be calculated by taking the formula for the wave speed, which is the distance traveled over the time taken, and rearrange the equation to solve for the time. For the oscillator to reinforce the wave and make a standing wave, the period of the oscillator must equal the time for the wave to travel the length of the string and back again. In this way, the period and frequency of the first harmonic can be calculated. The frequency is the inverse of the period. Now think about what would happen if we doubled the frequency or halved the period so that the oscillator makes 2 complete oscillations in the time it takes for the wave to travel to the end of the string and back again. As before, we'll do it slowly and keep track of what is going on. In the time it takes the oscillator to do half an oscillation, the wave has traveled halfway down the string. In another half period, the oscillator has done one complete oscillation and the wave has arrived at the clamp. Another half period later, the front of the wave is halfway back to where it started, now traveling leftwards. And as the oscillator completes 2 oscillations, the wavefront arrives back at its starting point. As before, this synchronization ensures that the oscillator is moving upwards as the wave arrives, and the wave is flipped from upside down to upright. Thus, the oscillator reinforces the wave through this synchronization. And as a result, we get another standing wave, the second harmonic to be precise. Now, here we should understand that because the oscillator completed 2 periods in the time it took the wave to travel there and back, we can say that 2t2 is equal to the there and back travel time. Thus, the period of the second harmonic is half the period of the first harmonic, and the frequency of the second harmonic is double that of the first. And we can keep on going. The next harmonic occurs when the oscillator completes 3 full oscillations in the time it takes the wave to travel there and back. This means the frequency of the third harmonic is 3 times the frequency of the first harmonic. The frequency of the fourth harmonic would be 4 times, and so on and so forth. This example of standing waves on a string clamped at both ends is a specific example of a more general fact about waves. If you send 2 traveling waves with the same frequency towards each other from opposite directions, their combined result will always be a standing wave. Let's look more carefully at what is going on here. In this example, there is a red traveling wave moving rightwards, as shown. Then there is a green wave traveling leftwards. Now, if you watch these two waves sliding past each other, you can see that there are points where they are out of phase with each other and cancel each other out, and there are times when they are in phase and reinforce each other. Now I will include the purple wave, which is the result of adding the red and the green waves together. You can see how the red and green waves slide past each other, perpetually alternating between being in phase, resulting in a doubling of the height of the peaks and the troughs of the purple wave, and then keep on going until they're out of phase, resulting in a snapshot where the purple wave is completely flat. Running this at regular speed, you can see how various points in the medium move up and down vertically, but the resulting purple wave itself does not move horizontally.